Let's be real. We are swimming in a sea of data. Sales figures, website clicks, survey results, you name it. But on its own, it's just a bunch of noise. The real magic, the skill we're going to dive into today, is how to take all that raw data and turn it into a compelling story, into a real discovery.
So, how do we become data detectives? How do we look at a massive spreadsheet and actually find the narrative that's hiding in there? Well, it all starts with one simple but absolutely crucial first step. Before you calculate a single average or run some fancy model, you have to use the most powerful pattern recognition tool you have, your eyes. Seriously, we're going to start by just looking at the shape of our data. And our first tool for doing that is the good old histogram. The best way to think about it is like a skyline for your data. Each bar represents a range of values. Think of it as a bucket or a bin, and the height of that bar tells you how many of your data points fall into that bucket. It gives you this immediate gut feel for where your data clusters and how it's all spread out. Now, this brings up a choice. A histogram is perfect for seeing the big picture, right? The overall shape. But what if every single data point really matters to you? For smaller data sets, a bee-swarm plot is just brilliant. It shows you the distribution, but you can still see every single individual dot. No detail gets lost. All right, you ready for a true secret weapon? This is a pro tip for all you data detectives out there, the empirical cumulative distribution function, or ECDF. Now, I know, it sounds super complicated, but trust me, the idea behind it is beautifully simple. So here's why it's so incredibly powerful. A histogram groups data into bins, so you lose a little bit of information. But in ECDF, it plots every single point. You lose absolutely nothing. Each tiny step up on that graph represents one data point. This means you can ask incredibly precise questions like, hey, what percentage of our customers are under 25 years old? And you can just read the answer right off the chart. It's amazing. So we've seen the shape of our data. Now let's put some hard numbers to that story. We need some key metrics that can summarize its core features in just a few figures. First things first, we need to find the center of our data. And most of us immediately think of the mean, the average. But it's got one major weakness. It gets totally pulled around by extreme values, or outliers. The median, on the other hand, which is simply the middle value, is way more robust. Just think of it this way. If a billionaire walks into a coffee shop, the mean income in that shop skyrockets, right? But the median income, it barely even budges. Okay, so beyond the center, we need to know about the spread. And that's where standard deviation comes in. Honestly, the easiest way to think about it is as your weirdness detector. It's a measure of how far your data points typically are from the average. A really small standard deviation means everything is clustered tightly together. It's all pretty normal. A large one means your data's all over the place. Now, if you want a ton of summary info packed into one single graphic, you cannot beat a box plot. Let's just break this down real quick. See that line in the middle? That's your median. Easy. The box itself, that contains the middle 50% of all your data. The whiskers show you the overall range, and those little dots floating outside, bam, those are your potential outliers. It's a whole story in one tiny chart.
Describing one variable is great, but the story gets so much more interesting when we start looking at how different variables interact with each other. Is there a connection here? Does one thing seem to influence another? Let's find out.
To measure this connection, we use something called the Pearson Correlation Coefficient, usually just called R. It's a single number that goes from -1 to +1, and it tells us how strongly two things are related in a straight line. Now, quick but super important warning. This measures a relationship. It does not measure cause and effect. It's the classic mistake to assume one causes the other, so always keep that in mind.
So when R is +1, you have a perfect positive correlation. Just imagine you're tracking ice cream sales against the daily temperature. On a chart, the points would form a perfect straight line going up. As the temperature climbs, sales climb right along with it, in perfect, predictable lockstep.
And if R is -1, it's the exact opposite, a perfect negative correlation. Think about training for a marathon. The more hours you train each week, the lower your final race time is going to be. One variable goes up, the other goes down. It's an inverse relationship, but it's just as predictable and just as strong.
Finally, when R is hovering around 0, your data points just look like a random cloud. There's no line you can really draw through them. Think about the relationship between your shoe size and your final exam score. There's just no connection, right? And finding no connection is a crucial discovery all by itself. It tells us these two things are not linearly related.
Okay, this is where our analysis gets superpowers. For real. We've described our data, we've found relationships. Now we're going to use those insights to build models of what could happen. Welcome to the world of probability.
You know, the world is fundamentally uncertain. Things are random. Probability is the mathematical language we came up with to quantify that uncertainty. It's how we make sense of chance and how we make really informed predictions about the future.
To do this, we use what I like to call story templates, or as they're officially known, probability distributions. The first one is the binomial distribution. It tells the story of any experiment that has only two possible outcomes, success or failure, that you repeat a fixed number of times. The classic example is flipping a coin 10 times and counting how many times it lands on heads.
So when do you actually use this? Anytime you have a yes-no outcome. The classic business example is loan defaults. A loan either defaults or it doesn't. So if you have 500 loans in your portfolio, the binomial distribution can help you calculate the probability of seeing exactly 5 defaults, or 10, or maybe a disastrous 20.
Our next story template is the Poisson Distribution. Now, this one tells a totally different story. It models how many times an event happens over a fixed interval of time or space, and its real specialty is dealing with events that are relatively rare. You use this one when you know the average rate of something happening. For instance, if a call center gets 10 calls per hour on average, the Poisson distribution can tell you the probability of getting a really busy hour with 15 calls. It's also perfect for modeling those rare events, like predicting the number of no-hitters in an entire season of baseball. So, we have these powerful story templates that can describe how random events might unfold. What's the ultimate payoff? I mean, what can we actually do with them that's so special?
We can simulate the future. By telling a computer the story of our data, whether it's a binomial story or a Poisson story, we can generate thousands, even millions of possible future outcomes. It lets us explore the full range of what might happen and understand just how likely each of those scenarios is. It is literally like having a crystal ball powered by mathematics. We've gone from just looking at data to summarizing it to modeling the very uncertainty of what comes next. These are the fundamental tools for making sense of a really complex world. So the only question left is, what hidden story is waiting in your data, and what are you going to do once you find it?